why temperature is not what you think. Put your hand on the table in front of you. Feel that solid surface, that sense of warm or cool against your skin. You think you're feeling temperature. You're not. You're feeling something far stranger, far deeper, and far more disturbing than anything your biology is equipped to understand. I'm Leonard Susskind, and after 50 years of working with thermodynamics, statistical mechanics, quantum field theory, and black hole physics, I need to tell you something that most physics teachers never explain properly. Temperature is not what you think it is. It's not heat, it's not energy, it's not even a physical thing in the way you imagine. Temperature is a confession of ignorance. And once you understand what that means, you will never look at the world the same way again. Let me start by destroying the most common misconception. Most people think temperature measures how much energy something has. Hot things have more energy, cold things have less. Simple, obvious, wrong, dead wrong. A bathtub full of lukewarm water has far more thermal energy than a lit match, but the match is at a much higher temperature. A spark from a campfire might be at 2,000 degrees, but it won't burn your house down. The entire ocean at 4 degrees Celsius contains more thermal energy than a lightning bolt at 30,000 degrees. Temperature and energy are not the same thing. They're not even close to the same thing. And the fact that we confuse them constantly reveals something deep about how badly we misunderstand the physical world. So what is temperature actually measuring? Here's where it gets interesting. Temperature is measuring something about information, about what you know and what you don't know about a system. And I realize that sounds bizarre. How can a number on a thermometer have anything to do with information? Bear with me, because this is one of the most profound ideas in all of physics, and almost nobody outside of theoretical physics appreciates it properly. Let me take you back to the 1800s. The Industrial Revolution was in full swing. Steam engines were powering factories. Engineers wanted to make better engines, more efficient engines. And a French military engineer named Sadi Carnot asked a beautiful question: what is the maximum possible efficiency of a heat engine? Not a specific engine, any engine. What does physics itself allow? Carnot figured out the answer in 1824, and it's still correct today. The maximum efficiency of any heat engine depends only on the temperatures of the hot source and the cold sink. Nothing else, not the fuel, not the design, not the materials, just two temperatures. That's it. This was extraordinary because it meant temperature wasn't just a sensation, wasn't just a number on a mercury column. Temperature was connected to something fundamental about the laws of nature, something about what is and isn't possible, something about limits that cannot be broken no matter how clever your engineering. But Carnot didn't know what temperature really was at the microscopic level. That understanding came later from a man who paid for it with his life, Ludwig Boltzmann, and his story is one of the most tragic in the history of science. Boltzmann was an Austrian physicist working in the late 1800s. He was brilliant, passionate, and deeply convinced that matter was made of atoms. Now, today, that seems obvious. Of course, matter is made of atoms, but in the 1890s, this was controversial. Many prominent physicists and philosophers, Ernst Mach in particular, argued that atoms were a fiction, a mathematical convenience with no physical reality. Boltzmann spent decades fighting this battle, and in the process, he discovered something that changed physics forever. Boltzmann realized that temperature is not a property of individual atoms. A single atom does not have a temperature. Temperature is a property that emerges when you have enormous numbers of atoms, billions upon billions of them, moving and vibrating and colliding in ways that are far too complex to track. Individually, temperature is what you get when you give up, when you admit that you cannot possibly know what every single atom is doing, and you instead describe the system statistically. With averages, with probabilities, with distributions, here's the key idea. Imagine a box full of gas, trillions upon trillions of molecules bouncing around. Each molecule has a position and a velocity. In principle, if you knew the exact position and velocity of every single molecule, you would have complete information about the system. You wouldn't need temperature at all, you just have a list of facts. Molecule number 1 is here, moving at this speed. Molecule number 2 is there, moving at that speed, and so on for trillions of molecules. But you can't know all of that. It's impossible, not just practically impossible, fundamentally impossible. The amount of information required to specify the exact state of every molecule in a glass of water is larger than anything you could ever store or process. So what do? You use temperature. Temperature is a shorthand, a summary, a way of saying I don't know the details, but I know the statistical properties, I know the average kinetic energy of the molecules. I know the probability distribution of their speeds. Temperature is the physicist's way of admitting ignorance while still making accurate predictions. And here's the part that should genuinely disturb you. The same physical system, the same box of gas with the same molecules in the same positions, moving at the same velocities, could have different temperatures depending on what you know about it. This is not a joke. This is not a paradox. This is what Boltzmann's statistical mechanics actually says. Let me explain. Suppose you have a gas in a box and you know absolutely nothing about the microscopic state. You measure the pressure and volume and calculated temperature, fine. Now suppose I give you some additional information. I tell you that all the fast molecules happen to be on the left side and all the slow molecules happen to be on the right side. The physical state hasn't changed. The molecules are in exactly the same positions with exactly the same velocities. But now you have more information, and with that information, you could in principle extract useful work from the system by letting the fast molecules expand against the piston. Your knowledge has changed what you can do with the system. And what you can do with the system is intimately connected to temperature and entropy. This is the deep secret of thermodynamics. It's not really about heat and work and engines. It's about information, about what is known and what is unknown, about the relationship between a physical system and an observer who is trying to describe it with limited knowledge. Temperature is not a property of matter in isolation. Temperature is a property of the relationship between matter and the observer, between the system and what you know about it. Now, I know this sounds dangerously close to philosophy, close to the kind of hand-waving that drives experimental physicists crazy, but let me tell you, this is hard physics, real physics. Physics with equations and predictions that we've tested 1,000,000 times over. Boltzmann wrote it all down in one equation, the most beautiful equation in physics, in my opinion, S equals K log W. Entropy equals Boltzmann's constant times the logarithm of the number of microstates. And temperature is defined through this entropy. It's the rate at which entropy changes when you add energy. That's it. That's the definition, not warmth, not heat flow, not the reading on a thermometer. Temperature is how entropy responds to energy, and entropy is a measure of how many microscopic arrangements are compatible with what you observe macroscopically. It's a measure of your ignorance. Boltzmann was so proud of this equation that it's engraved on his tombstone, S equals K log W. He killed himself in 1906, hanged himself while on vacation with his family. He was 62 years old. The scientific establishment had worn him down. Mach and his followers had made Boltzmann's life miserable, attacking his atomic hypothesis, questioning his statistical approach. Boltzmann suffered from what was probably bipolar disorder, and the constant intellectual battles pushed him over the edge. Within a few years of his death, Einstein's work on Brownian motion provided definitive evidence that atoms were real. Mach was wrong, Boltzmann was right, but he never lived to see his vindication. The man who taught us what temperature really means died thinking he had failed. Let me bring this back to the present, because the implications of Boltzmann's insight go far beyond steam engines and gas boxes. They reach into the deepest mysteries of modern physics, black holes, and this is where temperature gets truly terrifying. In 1974, Stephen Hawking made one of the most stunning discoveries in theoretical physics. He showed that black holes have a temperature. They radiate, they glow. Not brightly, not in a way you could see with your eyes, but they emit thermal radiation just like any warm object. This is called Hawking radiation, and it was completely unexpected. Think about what this means. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. It's the simplest macroscopic object in the universe. described completely by just three numbers: mass, charge, and angular momentum. That's it. No other details. No hair, as physicists say. The no-hair theorem tells you that a black hole is featureless, smooth, perfect. And yet it has a temperature. Why? Because temperature, as Boltzmann taught us, is about hidden information, about microstates you can't see. A black hole hides an enormous amount of information behind its event horizon. All the matter that fell in, all the quantum states of all the particles, all of that information is there, but inaccessible, hidden from the outside observer. And it's that hidden information, that enormous entropy, that gives the black hole its temperature. The temperature of a black hole is inversely proportional to its mass. The bigger the black hole, the colder it is. A black hole with the mass of the sun would have a temperature of about 60 billionths of a Kelvin, colder than anything in the observable universe. Colder than the cosmic microwave background, essentially undetectable. But a tiny black hole, one with the mass of a mountain, would have a temperature of billions of degrees. It would be blindingly hot, and it would evaporate, radiating away its mass as Hawking radiation, shrinking and getting hotter and hotter until it finally disappears in a burst of energy. This is where temperature connects to some of the deepest problems in theoretical physics, the black hole information paradox. When a black hole evaporates, what happens to the information that fell in? Is it destroyed? If it is, that violates quantum mechanics, which says information is never truly lost. If it's not destroyed, where does it go? How does it get out? I've spent decades working on this problem. My arguments with Hawking about whether information is lost in black holes are legendary in the physics community. I believed information is preserved. Hawking believed it was destroyed. Eventually, Hawking conceded. But the question of exactly how information escapes a black hole remains one of the greatest unsolved problems in physics. And at the heart of this problem is temperature. Because the temperature of a black hole's radiation encodes or fails to encode the information about what fell in. If the radiation is truly thermal, truly random, then no information escapes. But if there are subtle correlations in the radiation, tiny deviations from perfect randomness, then information could be leaking out in the most encrypted possible way. This is temperature at its most fundamental, not as a sensation, not as a number on a thermometer, but as a statement about what is known and what is hidden, about the boundary between accessible information and the information trapped behind an event horizon. Temperature is the universe's encryption key, and we're still trying to crack the code. But let me come back to everyday reality, because the strangeness doesn't stop at black holes. It's right here, in your kitchen, in your body. Everywhere you look, touch that table again. You feel it as cool or warm, but what's actually happening at the molecular level has nothing to do with what you feel. Your nerves are not thermometers. They don't measure temperature. They measure the rate of heat flow into or out of your skin. That's a completely different thing. When you touch a metal doorknob and it feels cold, it's not because the metal is colder than the air around it. The metal and the air are at the same temperature. They've been in the same room for hours. They're in thermal equilibrium. The metal feels colder because metal conducts heat away from your skin much faster than air does. Your nerves detect the heat leaving your skin rapidly, and your brain interprets that as cold. You're not sensing temperature, you're sensing heat transfer rate. Your entire lived experience of hot and cold is a misperception, a useful misperception, an evolutionary adaptation that helps you avoid burning yourself or freezing to death. But it has almost nothing to do with what temperature actually is. Here's another thing that will keep you up at night. Temperature can be negative, and I don't mean below zero on the Celsius scale. I mean genuinely negative on the Kelvin scale, the absolute temperature scale, where zero is supposed to be the coldest possible state. Negative absolute temperature. It sounds impossible. It sounds like saying something is colder than the coldest possible thing, but that's not what it means. And understanding what it does mean requires throwing away almost everything you think you know about hot and cold. Remember, temperature is defined as the relationship between energy and entropy. Specifically, temperature is inversely related to how entropy changes when you add energy. For normal systems, when you add energy, entropy increases. Molecules jiggle more. There are more possible arrangements, more microstates, higher entropy, the temperature is positive. But there are special systems, Systems with a maximum possible energy, where something strange happens. Once most of the particles are in the highest energy state, adding more energy actually decreases the number of available microstates. The entropy goes down when you add energy. And that means the temperature becomes negative. This isn't theoretical. Physicists have created negative temperature systems in laboratories. In 2013, a team at the University of Munich created a gas of potassium atoms at negative absolute temperature. And here's the truly mind-bending part. Negative temperature is not colder than zero. It's hotter than any positive temperature, infinitely hot. If you bring a negative temperature system into contact with a positive temperature system, heat flows from the negative temperature system to the positive one. The negative temperature object is the hot one. It's above infinity on the temperature scale, if that makes any sense. Which it shouldn't, because our intuitions about temperature are built for normal everyday systems, and they completely break down at these extremes. This connects to something I find endlessly fascinating about the nature of physical law. The laws of thermodynamics, the laws that govern temperature and heat and entropy, are not like other laws of physics. Newton's laws describe the behavior of individual objects. Maxwell's equations describe electromagnetic fields. Schrödinger's equation describes quantum states. These are fundamental laws about fundamental things. Thermodynamics is different. Thermodynamics is a theory about theories. It's a framework for dealing with situations where you don't have complete information. It's a physics of ignorance, and temperature is its central concept. The thing that connects energy to information, the macroscopic to the microscopic, what you can see to what you can't. The second law of thermodynamics says entropy always increases. Heat flows from hot to cold. You can't build a perpetual motion machine. These seem like laws about the physical world, and they are, but there are also laws about information. Entropy increases because systems naturally evolve toward states about which you have less information. Hot coffee cools down because the detailed arrangement of fast molecules in the coffee and slow molecules in the air gets mixed up, jumbled, randomized. The information about which molecules were originally fast and which were originally slow gets dispersed into correlations among trillions of particles, effectively hidden from you. The entropy goes up. The temperature equalizes. Information is lost, not destroyed, dispersed, hidden, made inaccessible. And this connects to the deepest question of all. The arrow of time. Why does time have a direction? Why do we remember the past and not the future? Why does entropy increase? Why does hot coffee cool down, but cool coffee never spontaneously heats up? The answer, as far as we understand it, goes back to temperature and the conditions at the beginning of the universe. The Big Bang was an extraordinarily low entropy state. The universe started in a condition of remarkable order, remarkable specialness. And everything that has happened since, every star that is formed, every planet that is cooled, every cup of coffee that has gone cold, every life that has been born and died, all of it is the universe sliding toward higher entropy, toward more disorder, toward thermal equilibrium. The ultimate fate of the universe, if current physics is correct, is heat death. A state of maximum entropy where everything is at the same temperature. Nothing flows, nothing changes, nothing happens. Temperature becomes uniform everywhere. And without temperature differences, no work can be done, no computation can occur, no life can exist. The universe becomes a vast, lukewarm, featureless void. Not cold, not hot, just tepid, everywhere, forever. This is what temperature is telling us about the fate of everything. Not through drama or violence, but through the quiet, inexorable equalization of energy. The universe is dying a thermal death, slowly over trillions of years, but inevitably, because the second law of thermodynamics, the law that governs temperature, is relentless. Now let me talk about something that connects all of this to quantum mechanics in a way that I find particularly beautiful and troubling. The vacuum, empty space. You think empty space has no temperature? You think the vacuum is at 0 degrees, absolute zero, nothing there, nothing happening wrong. The quantum vacuum is seething with activity, virtual particles popping into and out of existence, quantum fields fluctuating, energy borrowed from nothing and returned before anyone notices. And these fluctuations have a temperature-like character. They're related to the uncertainty principle, to the fundamental graininess of quantum mechanics. Here's the really strange part. Whether the vacuum has a temperature depends on whether you're accelerating. This is called the Unruh effect, discovered by Bill Unruh in 1976. If you're moving at constant velocity through empty space, you detect no particles, no temperature. The vacuum is cold and empty. But if you accelerate, if you fire your rocket engines and change your velocity, suddenly the vacuum is full of particles, warm particles, thermal radiation. The vacuum has acquired a temperature. The temperature is proportional to your acceleration. For accelerations we can achieve in everyday life, or even in particle accelerators, the temperature is fantastically small, undetectably small. But the principle is real. The vacuum's temperature depends on the observer. One observer says it's empty and cold. Another observer, accelerating through the same space, says it's warm and full of particles. Both are right. Both are describing the same physical reality from different perspectives. This is temperature at its most bizarre. It's not even a property of the stuff in front of you, it's a property of how you're moving through space-time. The vacuum doesn't have a fixed temperature. You give it a temperature by accelerating, by choosing a particular trajectory through space-time. Temperature becomes observer-dependent in the most radical possible way. And the Unruh effect is intimately connected to Hawking radiation. The mathematics is almost identical. A black hole's event horizon and the horizon experienced by an accelerating observer are deeply related. In both cases, the horizon hides information. In both cases, hidden information manifests as temperature. In both cases, temperature is not about energy or heat or warmth. It's about the boundary between what you can know and what you can't. Let me bring this full circle. You put your hand on a table and felt something you called temperature, but what you actually felt was a cascade of deeply mysterious physics. You felt the statistical behavior of trillions of molecules whose individual motions you cannot track. You felt the heat transfer rate determined by the thermal conductivity of the material, misinterpreted by your nervous system as a property of the object rather than a property of the interaction. You felt a manifestation of entropy, of hidden information, of the universe's relentless march toward equilibrium. Temperature is not a thing. Temperature is a relationship between energy and entropy, between a system and an observer, between what is known and what is hidden, between the microscopic chaos of atoms and the smooth macroscopic world we experience. When Boltzmann wrote S equals K log W on that blackboard, he wasn't just doing mathematics. He was revealing that the warmth you feel on a summer day, the chill of a winter morning, the fever that tells you your body is fighting an infection, all of it is information encoded, encrypted, processed by your biology into something that feels simple and obvious, but is anything but. Could I be wrong about any of this? Not really. This is established physics. Boltzmann's statistical mechanics is over a century old and confirmed by every experiment ever done. Hawking radiation is supported by multiple independent theoretical derivations. The Unruh effect follows from quantum field theory with mathematical certainty. Negative temperatures have been created in laboratories. The observer dependence of temperature is built into the foundations of modern physics. What we don't fully understand is why. Why does the universe have the particular initial conditions that give rise to the thermodynamic arrow of time? Why is the Big Bang state so special, so low entropy? Why does information hide behind horizons in a way that produces temperature? These are open questions, deep questions, questions that I've spent my career circling around without fully answering. But here's what I know after 50 years. Temperature is the universe whispering its deepest secrets to you through the simplest possible channel, through the feeling of warm and cold, through the reading on a thermometer, through the steam rising from your coffee. Every time you feel heat, you're feeling information being hidden from you. Every time something cools down, you're watching entropy win another tiny battle in its war to make the universe featureless and dull. The universe is information. Temperature is how that information expresses itself when you don't have access to the details. We live in a world built on hidden information, on secrets locked behind the limitations of what any observer can ever know. And temperature, this thing you thought you understood, this simple concept from childhood when you learn not to touch the stove, is actually the most profound expression of that hidden Architecture, you never felt heat, you felt the boundary of your own knowledge. You felt the edge of what physics allows you to know about the atoms in front of you. You felt the universe's information barrier dressed up as warmth. And that, I think, is far more extraordinary than any simple measurement of hot and cold could ever be. Thank you for listening. Now go touch something and think about what you're really feeling. Think about the trillions of molecules whose stories you'll never know, whose motions are hidden from you forever, and whose collective secret is the thing you casually call temperature. Think about that. Really think about it. And welcome to the real universe.